and have the recorder going, so I'll get that happening. And I'm going to go back from the worksheet back into the presentation. Okay, so we've done these. Make this slide a little smaller so we can see it. And then now we're ready to start in with what is actually a voltaic cell. So what I was saying before, that our oxidation reduction reaction was happening in a single container, but with a voltaic cell, it's going to be in two containers. So on one side, our reaction is going to be copper solid, and that's going to become then copper 2 plus and 2 electrons. So that is an oxidation, and it's happening in this container on the left side, and that container is called the anodic half cell. It can also be called the anode, although that's usually just what you call the electrode. So up here is the copper anode electrode. On the other side, on the right side, now we have silver cation, so Ag plus. And then if we give it an electron, like that, then that's going to cancel out our positive charge, and now we're going to have silver solid. So notice in each case we do have the solid present. We've got the copper over on the anode side, and we've got the silver present on the cathode side. Now over here is the cathode, and the cathode is where we have a reduction. And we also have the cations on both sides. We've got the copper cation over on the anode side, the left side, there it is. And then we've got the silver cation present on the cathode side, the right side. All right. Now, sometimes people have trouble remembering, between anode and cathode, what goes with oxidation and what goes with reduction. And one thing that has been put out to help people remember that is to use the word, or the little saying, oil rig, because what that is doing is oxidation is going to be a loss of electrons. And then the reduction, which is on your other side here, that's going to be the gaining of electrons. Now that'll help to keep it straight as far as the gaining or the losing and the gaining. But the other thing is, how do we keep these words like anode and cathode straight? Well, if we look at the anode, you notice that it starts with a vowel, and so does the name for it. So anode, oxidation, they both start with vowels. And while that's not a scientific way to remember it, it will help you keep it straight. And then on our other side here, cathode and reduction, they both start with consonants, and so you can keep those two together. Now, a couple other things I need you to catch here. On the left side, the anode side, we are producing some electrons. right here, 2 electrons. The electrons are flowing from the anode over to the cathode. And there's an arrow up here on the top. So you need to remember that where the anode is, where the oxidation is, the electrons are going to be flowing away from that side and over to the other side. Okay? And you can almost think about it as going counter or going clockwise around. Now, if we then look at the cation, down here is the copper 2+ cation. And when it comes away from the copper electrode, think about it as coming up to the salt bridge, which is this thing here in the middle that connects the two sides together. Well, if it comes over there, inside the salt bridge is sodium cations. So that's Na+. Well, we can just forget about them being sodium, really, and just consider their charge. So they're positive. So that positive charge is moving from the left over to the right side, over to the cathode. And then when the sodiums get down here to the bottom of our salt bridge, they're going to be pushing then the silver cation, which is positive, over towards the electrode. So that completes our circuit. So the voltaic cell, the galvanic cell, is not going to work unless you have a connection between the two separate sides of the process. Let's see, one more thing, and that is this electrical potential that we see at the top here, the positive 0.46 volts. The potential should always be positive. It should always be greater than 0 for a voltaic cell or a galvanic cell. It means the same thing. If it's positive, then the process is going to be spontaneous, and it's just like what we did in our thermochemistry chapter, where in that case we want a negative value for our Gibbs free energy to make it spontaneous. But if it's an electrochemical cell, we want the potential to be positive. Now you may be wondering, well, what's all this about? What do I have to actually know from this picture? Well, you need to know that, oops, get my marker going. You need to know that you've got an anode, that's going to be an oxidation, and electrons are going to flow away from that electrode. On the other side, the electrons are going to flow to the electrode. That's going to be the cathode. That's where the reduction occurs. And then you're going to have your positively charged ions moving through the salt bridge from left to right. So you should be able to label something like this if you see it again. And you should know something about the flow of the electrons and the flow of that positive charge. Okay? Anybody got a question? Okay, let's go to our next slide then. So on the next slide, this is just focusing really on the salt bridge. And you have this phrase here, salt bridge maintains the charge balance. The idea is if you didn't have a salt bridge and you were making these copper cations, if they could not go over to the salt bridge and push the sodium cations to the other side, then they would just be piling up there, is a way to think about it. And then on the other side, if we weren't pushing the silver over to the electrode, then you would have a loss of those positive charges on the other side. So you can't be throwing charges away. You can't be saving them up. They have to just keep moving. And the salt bridge is what's going to accomplish that, along with the wire. Okay, let's go to a little bit different voltaic or galvanic cell. This one's got different materials in it. I'll make this a little bigger. I'm having trouble seeing it. There we go, that's better. In this particular galvanic or voltaic cell, on the anode side, where the oxidation is happening, there's a piece of magnesium. So that's what this coil is here. Now you're also going to have some magnesium cations in there, some Mg2 plus cations. And then what we have going across the top here is, because of that reaction of magnesium producing Mg2 plus and 2 electrons, we're going to have electrons flowing from the left side over to the right side, just like we did before. And then on the right side, there's going to be a reduction. We're going to use those electrodes. Sorry about that phone. And we call that side again the cathode or the cathodic half cell. But now there's a little bit different in what's happening with this one. That is, the electrode is made of platinum. It says up here, platinum wire. Well, platinum doesn't react in a electrochemical sense. It's not going to lose electrons. It's not going to gain electrons. It's just really kind of inert, doesn't react. So its purpose is not to participate in any sort of reaction, but it's just simply to get the electrons down into the solution here. And in that solution, though, we have hydrogen ions, H plus. And the hydrogen ions, the H plus, can pick up an electron and it can get reduced. But what we're wanting to end up with is hydrogen gas, because that's, the elemental form of hydrogen. So for that to happen, we would need 2 hydrogen ions and we would need 2 electrons for that to work. So that's what's going to go on inside our solution here on the other side, is that we're going to be taking the hydrogen ion, the H plus, and converting it into hydrogen gas. And it's not so easily to see, but on the right side here, there are bubbles, and that is the hydrogen gas that we're producing from the hydrogen ion. We still have the situation with the salt bridge. We still have a positive charge that has to move from the left to the right in order to balance things out. So this is just a different voltaic cell, different combination of materials involved. This time we've got magnesium and we've got hydrogen ion. Now at the bottom here, I'm going to erase for a second. Well, unless somebody's got a question. Okay, I'm going to erase, and I want to talk about what we see here at the bottom. So this down here is a shorthand way of representing what we have in the picture above. So this is going to give us a representation of what we see up there. And here's how it's going to work. It starts out with whatever is your electrode over on the anode side. So that's magnesium solid. And then we said that magnesium solid is going to get converted into magnesium cation, Mg2 plus. Now the reason why there's a vertical line is to represent that there's a difference in the state of these materials. the magnesium is solid. The magnesium 2 plus is in an aqueous solution. So to illustrate that, we have a vertical line. We then get to the salt bridge, and you can think about the salt bridge as having one end in one beaker, the other end is in the other beaker, and those two ends are these two vertical lines that we have. Then once we get into the cathode side, over on the right side, we're going to have a hydrogen ion that's dissolved in water. So it's H plus AQ. And then I drew the reaction out before that you're going to be producing bubbles of hydrogen gas. So that's this part here. Again, we've got a vertical line because you're going from aqueous solution to a gas. But to finish it out, we got to get to our last electrode, which is the platinum, inert platinum electrode. So we write that in, and then we put in a vertical line. So what you need to be able to do is, if you have a picture like what we have here at the top, you should be able to take that picture and write out the shorthand version of it. Or if you have the shorthand version of it, you should be able to figure out, well, what does that look like? So that you can go back and forth between the two. Has anybody got a question on doing that? Okay, not seeing anything there, so we'll move on. And let's see, before we do that, well, no, we'll go on ahead. So on this next slide, we have something called a hydrogen electrode. And that's like what we had in our previous slide. We have got hydrogen ions in there, and I'm not seeing it written out, but there is H plus down in the solution. And that's getting converted into hydrogen gas up here. And we have another inert electrode. It's platinum. It's this wire that's coming down to a piece of platinum at the bottom. And that's just a way for electrons to get either out of the solution or into the solution. They can flow either way, whatever they need to do. Now, we're making hydrogen gas from the H plus, but we also are supplying hydrogen gas. That's what this up here is showing us. So that we're trying to achieve a controlled amount of hydrogen gas, and we definitely have a controlled amount of the hydrogen ion. And then that is sort of creating us a equilibrium between them, and the equilibrium is getting perturbed by whatever is going on with the wire. So we have a magnification of the process that's happening at the electrode, and that is either a hydrogen ion like you have up here, H plus, is going over to the electrode and it's picking up an electron, and then it's coming back out. Two of those are, that's the other one down here. And then those are coming out as hydrogen gas, H2. But like I said, electrons can flow into the electrode or they can flow out of the electrode. So that's what's occurring down below what we see at the top. We have hydrogen gas coming up to the electrode. It's losing an electron and it's becoming H plus, and it would actually become two of those H pluses. Okay, so you're probably thinking, well, why do we care about this thing? And here's the reason why. If we go back to one of our early pictures here, on our voltmeter, we've got this 0.46 volts. Well, part of that 0.6 volts is coming from the anode. Part of that is being caused by what the anode is made of. But it's also being caused by what the cathode is being made from. You know, so for the anode, we have the copper, and for the cathode, we have silver. And we don't know how much the copper and the silver are contributing to that number of positive 0.46. We just know that some of it's coming from the copper reaction and some of it's coming from the silver reaction, but we don't know how much is coming from either one. So the only way we could figure that out really, really the only way we could ever figure that out is to replace each of these electrodes with an electrode that we absolutely know what its contribution is potential. And that's what the hydrogen electrode is going to do for us. When I go here, and then I go one more, this is a hydrogen electrode. And, well, I think that was on the previous slide, sorry. Oh, I see why. It's down here. Whoops. For the reaction at a hydrogen electrode, everyone has agreed that the potential is going to be 0 volts. So if the potential of the hydrogen electrode is 0 volts, then whatever we see on our voltmeter has to be only due to the other half cell. So now we can look at this next page. In this case, we've got a hydrogen electrode over here. But on the right side, we have copper solid in that strip, and then we've got copper 2+ cation. So what we're measuring here is the potential from the copper, not from the other side, the hydrogen electrode, because we're saying its potential is 0. So what we're getting here is Cu2 plus 2 electrons, making copper solid. And so this number over here, positive 0.337, is because of this reaction, because for the hydrogen electrode, its potential is 0. Now let's look at another example. We do have the shorthand representation down here, like I was talking about before. So here we have, oh, yeah, Lily, what's up? Talk or type?
I was gonna say, why is it 0 volts for the one on slide 9? I was trying to get it, but I don't think I got it.
It's because we've just agreed that that's what it's going to be.
Who agreed?
The scientist.
Oh!
You and I and everybody else is supposed to agree with them, but several years ago, they developed a hydrogen electrode, and they all decided, hey, this is going to be 0 volts. Now, there is a theoretical reason for it being that, but we're not going to get into that.
So anytime we see a hydrogen electrode, it's 0 volts? Is that what that means?
That is absolutely correct, yes.
Okay, thank you.
You betcha. And you can see why we're doing that, so that when we compare it to something else, we don't have to worry about, well, what is it? Well, it's 0. Okay, so now let's go on this other one here, where now we have silver. So I've got a silver cathode, silver electrode. I've got silver cations out in the solution. So the reaction is going to be Ag plus 1 electron is going to make silver solid. So the number that we're seeing here at the top, the positive 0.8, is because of this reaction only. Because as we were discussing there, the other side where we have the hydrogen electrode, its potential is 0. So the number that we're viewing is just for the silver electrode. And again, we've got this written out in the shorthand version. Now, for this to work, we've got a couple of things that we have to consider. And that is, this is only true if the concentrations of the cations that are involved is 1 molar and that the temperature we're doing this at is 25 degrees C. If it's something different, then we would have to check for it, and we'll talk about that a little bit later on. But now, what I want to do is take these two reactions. So we've got copper, positive 0.337, and silver, positive 0.80. And I want to go to this slide here, and I'm going to make it bigger so you can read it somewhat better. Okay, so looking down here. So here is our silver. And so it's silver cation plus 1 electron makes silver solid. And so, some people have done the experiment with the hydrogen electrode and found that, hey, it is a positive 0.80. Now let's then move down and see if we can copper. So here's copper. Cu2 plus 2 electrons becomes copper solid. Its potential is a positive 0.34. Again, that would have been measured versus a hydrogen electrode that had a potential of 0. Now, what we could also do is if we knew that the copper was 0.34, we could make a electrochemical cell that has copper and has silver, and we could predict what the outcome should be. We're going to get to that in the next slide. I want to say a little bit more about some of the stuff on this slide, though. So I need to make this smaller so we can see more of what's going on. We'll go to the top here. At the top here, we've got fluorine gas. And we're taking fluorine gas and we're making it into fluoride. So in order to do that, our potential is positive 2.87. This is one of the strongest oxidizing agents there are. Now let's go down to the other end of our table. Down here we've got lithium solid. And we're going to take we're going to take a lithium cation and we're going to make it into lithium solid. And its potential is a negative 3.05. It is the strongest reducing agent. So if we had to compare different materials as far as how well they oxidize or how well they reduce, we could look at their numbers. Whichever one is more positive is a better oxidizing agent. Whichever one is more negative is going to be a better reducing agent. And again, remember that what it means when it says reducing agent is that it's going to give up electrons, or it's going to lose electrons. You know, it's that friend that has all the money, can give up electrons. And here on the other end, the more positive one, when it says the strongest oxidizing agent, it means that it can take electrons. Okay, So that's what it means when it says reducing agents and oxidizing agents. Now we got one more thing we want to get off of this table, and that is, if I make it a little bit smaller so we can see a little bit more of it. In the middle, we have hydrogen peroxide, H2O2. Hydrogen peroxide can be either. It can be an oxidizing agent or it can be a reducing agent. It can get oxidized, it can get reduced. It can go either way. And it's in the middle of the table. So if you were ever asked what material could be either an oxidizing agent or a reducing agent, and you have a table around, and you look in the middle and you see hydrogen peroxide, you should say, oh, it is going to be hydrogen peroxide. Everybody got that? Okay, so now we're going to take these potentials. And the thing about them is they're all for reductions. It's always going to be, when we've got these numbers, it's going to be taking something, say, we'll just generically say M plus. And we're going to add to that however many electrons we need to. And we're going to end up then with M that no longer has a positive charge. And in most cases, it's going to be something that's going to be solid, although there are some other possibilities of what you can end up at. Okay? So these are always going to be reductions. These are always going to be where the material is gaining an electron in one of these tables. But the thing is, like if we go back to our voltaic cell that we started at over here, no, almost, there we go. That in our voltaic cell, one side is going to be an oxidation and one side is going to be a reduction. So this side that's the reduction is the same kind of reaction as what we have in our table. But the other side, where you have the oxidation, that's the opposite reaction. So instead of giving it an electron is coming away from it. So that's going to show up in the math that we're going to do in just a moment here. So let me come back over to that. And here we go. So this is the cell potential equation. Not going to be given. I'm sorry. You guys will have to remember it. And so what it's saying here is that you take a reduction potential for the electrode that is the cathode. And then you take a reduction potential from our table for the anode, the other electrode, and you subtract it. You want to remember that you're going to subtract it. And then that would allow you to calculate what your voltaic cell potential is. So here are the two entries from our table of reduction potentials. We've got copper 2 plus becoming copper solid. Its potential is positive 0.337. The next one we have is silver. It's getting reduced to silver solid, and its reduction potential is 0.8. Now, let's say that we don't know if the copper is the cathode or if the silver is the cathode. We don't know which one is which electrode to begin with, but we do know these potentials here. And the other thing that's important is that for it to be a voltaic cell like we're talking about, then it's going, the result of the calculation is going to have to be greater than 0. Okay? Doesn't matter what number it really is, but it has to be a positive value. So what we can do is try these two numbers where we try one as the cathode and one as the anode. So that's what we did right here. We tried the copper as the cathode we tried the silver as the anode, and we got a negative number. Because we got a negative number, we say, oh, that's not right. So we're drawing a line through that. We come back and do it again, but the second time now, we're using the silver reaction as the cathode, so the positive 0.8 there, and then we're using then the copper as the anode over here. And this time we get a positive value. Positive value. So that means now that we have figured out what is the cathode and what is the anode. Because if we have the 0.8 as our first value, then it is the cathode. If we have the 0.337, then that is the anode. Okay? So it's just, you can try it one way and then try it the other. I mean, you may be able to just see which way it's going to go before you even calculate, but sometimes you just go ahead and do it and see whether you're getting a positive or a negative number. Next thing I want you to do with this, though, is to take the two reactions that we have up here. I'm going to erase this, it's getting a little busy. I'm going to take these two reactions, I'm going to take these two reactions and figure out what are the actual reactions that are happening. Well, we decided here that because because we're using the 0.8 as our first value, that must be the cathode. And that's going to be reduction. So that's the silver. So coming down here, the silver cation plus an electron becoming silver solid. We're going to take it as it is. It's going to be a reduction, and we know that reductions are the cathodes. And then if we take then our other value, this time the 0.337, that's the copper. We come down here, we flip around how we're writing it. So instead of starting out with the copper 2 plus on the left, we're writing it with the copper 2 plus on the right. You know, I'm comparing to what we have up here. So you start out with the copper 2 plus. Excuse me, I think I just said that backwards. Yes, I did. I'm sorry. We want the copper 2 plus on the right, so we're going to start out with the copper solid on the left. And so this is the reaction that's actually happening in our voltaic cell. And so that's the anode, and that's the oxidation. We're going to do this on a worksheet, and I think once you do it on a worksheet, it's probably going to be easier to see than me trying to explain it. Now, the last thing we want to do is take these two reactions. I'm going to erase again. We want to take these two reactions right here, and we want to combine them together to get an overall reaction for what is happening. So I take the copper. Well, wait a minute. Before I do that, erase again. Before we can do anything, we need to look at the number of electrons. And you see that for this first reaction, I have 2 electrons, but for the second one, I only have 1. So I'm going to need to take that entire reaction and multiply it by 2. So that I'm going to have 2 silver cations, I'm going to have 2 electrons, and I'm going to have 2 silver solids in my final result. So now let's take that information and try to construct an overall reaction for what's going on. I'm going to change colors. Okay, here we go. Copper solid. Copper solid. 2 silver cations. 2 silver cations. I could have put in the 2 electrons. I'm going to write it below here. The 2 electrons that I have right here. Then I'm going to come over to the other side here. I've got a single 2 plus cation, so there it is, Cu2 plus aqueous. And then I've got, oops, somebody going to say something? Nope. Okay. So I'm going to take the 2 electrons here and I'll write it below here and show you why I'm not including them in the reaction. And then I've got 2 times the silver. So that 2 that I have over here, it applies to the silver solid that I have there. So I've got 2 silver solids. I write in 2 silver solids. So this is the overall reaction that's occurring. Now, since I have 2 electrons on the left and 2 electrons on the right, I can draw a line through those. I don't need to keep them. And that's why they are not in this reaction up here that we derived. So anybody got a question on how we get there? You're going to do it on a worksheet, but I want to see if you guys got a question before we do that. Okay, I think we got one more slide we should take a look at. Yeah, we do. So we'll go to one more slide and then we're going to do the worksheet. So this is the first voltaic cell slide that we saw. And this is for that same calculation we were just doing. So you can see that again, I've got positive 0.46 just like we calculated. And I've got the copper as the anode where you have the oxidation. And we have the silver as the cathode where we've got the reduction. Okay, so that fits with our calculation we were doing a moment ago. So has anybody got a question before we go to the worksheet? Okay, looks like we don't. So before we do that, okay, let me show you where the worksheets are just to make sure that you can get there. So I'm going to share my screen. I'm going to go to Blackboard. I'm going to go down to course materials. And I'm going to go to worksheets right here. Click on worksheets, scroll down a little bit till I get to electrochemistry, click on that. And now we're doing the standard cell worksheet, the diagram here. So let's see. We'll start out down, oops, we'll start out down here. And then we'll just go around, you know, something like that. So I'll just call on some people to do that. We'll see how that goes. So I'll get the old random thing here happening. Jamie, can you write in here what the answer is, please? I think it'll let you do it. You see how hard it is to write on this thing? It kills me most of the time. Yeah, that's good. Oh, by the way, guys, you see at the top there where there is a T? If you click on that, it'll let you type. You just have to click in where you want it to be. So let's do that. We'll do that for the next one. So we're going to go to this one right. We're going to go to this one right here now. So I'll call somebody else. Shaniqua, would you type in here what you think the answer ought to be. Guess I should make sure she's still here. Uh-oh. I think, yeah, her connection died. Okay, let me call somebody else. Congratulations, Lily. It's you.
So I hit this pencil thing so I can write
No. Go over two more to where you got the T,
the T. Oh, this thing. Okay.
and then you click in where you want it to type, and then you type, and it should type it in there for you. Let's see how that
And
looks.
I'm doing this one up here.
You're doing this one down here.
Shoot, I can't see where you're showing me. Let me zoom back.
It's right above where she put in the not Excel.
This one? Okay. This should be AL anode. And I just hit enter.
Let's see. Yeah, that's how you do it. That wasn't really the one I was wanting you to do. I was wanting you to.
I
Hey,
couldn't see which one you want.
I know. Hey, it's okay. It's not that big of a deal. I'm going to see if I can make that larger so we can read it a little better. There we go. Hey, not too bad. Okay. Now I'll get somebody to do the one that's right below that. So, Erica, would you type in right here? Oops. Got to click on something first. Could you type in right here what that is, please? Out of that list that's above everything. Hmm. Thank you. You can hear me. All righty. I'll make
Oh,
that.
that's what goes there.
Yeah.
I didn't know it went there.
Oh, wait a minute. No, is that what we want?
I
Are
don't
you
know.
sure that's what you want? If it's an aluminum anode up here at the top, oops, let's get the marker going. If it's an aluminum anode up there, what's down here in the solution? That's what it's asking. So I'll tell you what, I'm going to take that out. And yeah, I see what you want there on the text. I'll tell you what, I'll put it in for you. How about that? So, okay, click here and go AL3 plus. Well, I wish I could set it to type bigger because it is so hard to see, but that's what you want, AL3 plus there. Okay, so now going across the top here, we need to put in what is at the top. So I'll get somebody. Crystal, would you type in that box what that is going across? I marked the box. You can just pick something from that list above there. See, all these answers are coming from up here. know she's hearing me because I'm just sent her a chat. I'm not getting anything back. I'll go to somebody else. How about Victoria? Let's see. I think, yeah. Hey, Victoria, could you type in here on that list what you think the answer is? You just click on the T at the top and then click into where you want it to type at. Okay, I seem to be failing on this idea. Let me try one more person. Hey, Stephen, could you do it for us, please? Just click on the T at the top and then click where you want it to type at. See, I figured you guys would like to do it this way because you never get to, write on the board. Oh, there we go. He got it. Thank you. So electrons flow to the right on the wire. Okay. Well, we are slowly making progress across here. Let's go over to this one. I'll ask somebody. Delani, if you can hear me, would you please type in that box what you think it is? This box right here. You just click on the T and then click in the box and type what you want. Yeah. Okay, I'll make it bigger. Oops. What I'm doing is I'm using the oops. I click on it with the arrow tool and then you can expand it. So we got zinc solid for that electrode. So now we've got this, oops, we got the one right below it. So I'll get someone for that. Imsada, would you please type in the box here what you would call that from this list that you have above? Aha, thank you. So we've got 1 molar zinc 2 plus in the solution down there. So now everyone's getting really bored out of their minds, so I think I'll just finish this off. So down there, we've got the cathodic cell, cathodic half cell. There we are. And for this one up here, the answers that this worksheet had on it was the anions flowing from the left, which does make sense. The anions are going to flow, flow from the right. They're going to flow from the right. But really, it's more important to track the cations. But it would be correct to say that anions flow from the right. Then the cations, which is really more important, they're going to flow from the left. So this here is talking about, let me get my pen. This is basically saying, well, the negatives are going to flow this way. And that does make sense as far as the electrons going around and then they're negative. But what's maybe more important is that the cations, the positive ones, are going in the opposite direction. Okay, has anybody got a question about this worksheet? Yeah, Lily, what's up?
How do we do the shorthand?
Oh, yeah, I forgot about that.
That
Okay.
one's hard.
Oh, it's not hard. No, what you do, let me erase everything so we got a clear picture here. What you do for those is you start out with your anodic electrode. So I'm going to change my pen to red. So you're going to start out, I'm going to number these. You're going to start out there is 1, then you're going to go to the solution is going to be 2, and then the salt bridge is going to be 3, and then the fourth thing is going to be the solution on the other side, and then your cathodic electrode is going to be your fifth thing. Now that's for one of these typical kinds of voltaic cells. Now we had some that involved like hydrogen gas and some other stuff and inert electrodes. Those are a little more complicated. So this is set up to where you've got one vertical line, a pair of vertical lines, and the pair of vertical lines is representing the salt bridge. And then you've got one more vertical line. So what you're going to wind up doing is putting in the aluminum, no, not aluminum. Sorry, no, it's not aluminum. What am I doing? Yeah, it is aluminum. Sorry, I was not thinking. So you put in the aluminum solid here as your first item. And then your aluminum cation, so the aluminum 3 plus is going to go here. Now, of course, we're supposed to be putting solid and aqueous and all that stuff in there too. And then on the other side of the salt bridge, we've got the zinc. So that's going to go here. Oh, I keep losing my marker. Zinc 2 plus is going to be there. And then you're all the way back to this other electrode, and that is going to be zinc solid. Does that make sense?
Yes, thank you.
Yeah, so you're following that way around the diagram. Okay, I'm going to kill that. And let's see, let's go back to the PowerPoint. And we'll proceed from there. So this is basically what we were working on that worksheet was we were using this equation in order to get the potential of the cell, but also in that process we're identifying what's the cathode and what is the anode, because we were trying to arrange these so that we get a positive value. And then once we know what is the cathode and what is the anode, we can take whatever is the cathode and we can leave it as a reduction like you have down here. See, silver is the cathode, You leave it as a reduction reaction, just like it was originally written. Then the other reaction has to be then the cathode, so that is the copper one. So that's going to go up here. I think I said anode, I don't know. Anyway, I meant to say anode. That's where the oxidation is going to occur, and then for that one, we have to flip it around. So we have to take the products, make them into reactants, take the reactants, make them into products. Okay? And then we can combine those two reactions that you have together and get the overall reaction for that particular process. Okay, so now let's go back for just a second. Remember, I was saying that for this to all work out, we have to have 1 molar solution, 25 degrees C. Well, it's not always going to be that way. In fact, when we did the lab, the voltaic cell lab, you had an example of where you did not have standard concentrations. So in order to deal with that, we're going to use the Nernst equation, not the Nerd equation. And we've got two versions of it. The first one is what you're going to use if we are dealing with the concentration not being 1 molar, and also if we're going to deal with the temperature not being 25 degrees C. Now, if you were going to use this equation, you would have to put the temperature into Kelvin. Okay? Now, the thing is, we're not going to do the case where the temperature is not standard. So we're not going to have to worry about this first reaction. We're only going to do the second situation where all that has changed is it is not 1 molar. But the temperature is equal to 25 degrees C. Okay, so I'm not going to get into the explaining this first one here. We'll just go to the second one. And this equation is provided. You're not going to have to memorize it, okay? It's provided in most cases. Had we been using the ACS standardized exam, it's provided there. I'll provide it, on any exam you have. And I think that any time you'd run across this, they would give you the equation. So here's what's going on. There's two things you're going to have to do to use this equation. And otherwise, it's not that big a deal. But what you're solving for is what is the potential, what is E, if the concentrations are not 1 molar. So the things that we're going to have to do is figure out what is Q and what is N. Once you know those, you can put them into this equation and then you can simplify it, and it's not really that big a deal. So the reaction that we're going to use as a model is this reaction. We've got iron 3 plus. We're going to give it 1 electron, and it's going to become iron 2 plus. So we're taking it from 3 plus to 2 plus. Now, the standard value is this number, 0.77 volts. So that's what we're going to use for this, the standard value. It's going to be positive 0.77. But then we need to figure out what is N. And N is the number of electrons. It says that up here, number of electrons transferred. So for this example, it's only 1. You look here, that's 1 electron. So we come down below and you see that we've got a 1 right here. That's where that 1 came from. There's only 1 electron involved. Then the last part is figuring out what Q is so we can take the log of it. And Q is the same Q that we used when we were doing equilibrium. So it's going to be the products over the reactants. Oh man, my writing here is pretty bad. Products over reactants. So we are going to take the two concentrations. So our product is the Fe2 plus. So down here below it says, okay, the concentration of the Fe2 plus is 4 molar. So that's where this number comes from. Then our reactant is the Fe3 plus. And we're told that the concentration of the Fe3 plus is 2 molar. So that's where the 2 is coming from. So we're just taking 4, dividing it by 2, and we get 2. And that's what we're going to be taking the log of. So that's why down here it says log of 2. So now we've got the 0.0592 divided by 1, so it doesn't change. And then when we take the log of 2, we get 0.301. So it's getting fairly easy. We're going to take the 0.0592, multiply it times the 0.301, and then combine that with the standard potential, the 0.77. And your result then is 0.75. So cleaning this up a little bit, the things you got to remember is, where did we, oh, it's given up here. Okay, pen going. It's part of the equation, the 0.0592. It's combining the gas constant and the standard temperature, and also Faraday's constant, which we didn't even get into. That's where the 0.0592 comes from. But the more, the bigger deal is figuring out what N is, and that is how many electrons are involved. In this case, it's only 1. And then what is Q? And Q is, like I was saying earlier, it's going to be the products over the reactants. So we just have to look at our equation. This is the reactants. This is the products. We take the concentrations that are given, plug them in, and you're just taking a log of that. So you guys good with that? Anybody got a question? Okay, we do have a worksheet on that, but I think I would rather just keep going right now, and maybe we'll come back and hit the worksheet a little bit later on. Okay, but does anybody have a question? Oh, where did the F go? Well, the F wound up in the 0.0592. So the R, the T, and the F all became 0.0592. The R is the gas constant, the T is 25 degrees in Kelvin, and F is Faraday's constant. Okay, everybody good with that? So then let's move on. So we have been doing voltaic or galvanic cells that are spontaneous, but there are times when we are going to be seeing non-spontaneous electrochemical processes, and those are called electrolysis. So instead of having a voltmeter up here, we've got a voltage source. So we're not going to measure the voltage. We're going to make the voltage to be a particular value. And then what we have below here is two electrodes. As usual, we got an anode and a cathode. We're going to be doing an oxidation at the anode, as usual. We're going to be doing a reduction at the cathode. But we're going to be forcing those to happen. It's not spontaneous. This is a way to make chlorine gas and to produce sodium metal. Both of those have economic value, so that's why we would do it. You start out with sodium chloride, and we heat it up to 801 degrees so that it melts. So now we got molten table salt, or molten sea salt is what they would actually be using, something cheap like evaporating the water out of salt water. And then you would just have the sodium chloride. Heat it up to 800 degrees, have these two electrodes and a source of power. And our salt bridge this time is a porous screen. It would be like a piece of porcelain that has very small holes in it. So we heat it up to 800 degrees, and then what's going to happen on the anode side is we're going to oxidize chloride, and we're going to make it into chlorine gas. And then on the other side, we're going to reduce sodium cation into sodium metal. So you'd have chlorine gas bubbling out. They're showing that there. And then you would be getting a layer of melted sodium on the bottom. And you'd do that for a while and then stop it and then take the sodium out and use that to sell it. So this is used for some other ways of making materials. Zinc it's a common way of doing it. It's the way we get aluminum. So those are all of the similar kind of processes. Now another kind of electrolysis is on the next page here. Again, we don't have a voltmeter, we've got a voltage source. We are making the voltage a particular number. And then we have in our container up here water that we've put a little bit of acid into. And then what's going to happen is we're going to be doing a oxidation on one side, and we'll be producing then oxygen gas from the water. And on the opposite side, where the cathode is, we're doing a reduction, and we'll be producing hydrogen gas. And this is, well, it gets used for some things, like on the space station and the space shuttle, they save all the water that is, this wastewater, not the water they're going to drink, and they'll then use that to produce oxygen for the crew cabin. So it does get used there. It gets used on submarines for a similar reason. Can't think of another application, but those are the two to where it's a practical thing to do to get oxygen and hydrogen from water. Now the next slide is using this. This time we're not going to even separate into two solutions. We're just going to have in here silver nitrate, and we're going to have a bar of silver. And then we'll have a voltage source at the top, and then we attach to the other side of the voltage source, for instance, a spoon that we want to make it appear to be silver. So this is not, the spoon is not really silver all the way through. The spoon is actually probably just made of steel, and we're going to give it a coating of silver on the outside. And this is actually done in some cases to create a silver plate on the outside of a steel object. In let's see, up until about the 1970s, a lot of the parts of automobiles had a coating of chrome on the outside of the steel, the bumpers, the door handles, various parts. And they would apply that using a similar process. So they would put a chromium metal on the outside of the bumper to make it shiny and to keep it from rusting. Now you'll see things that look like it's chrome, but in many cases it's just plastic that's got a material that looks like chrome, within the plastic layer. So they don't really do this anymore in the automobile business. It's just too expensive. Okay, this gets us to Faraday's constant that I mentioned earlier. And what Faraday is doing, what this constant is doing, is it's taking the number of electrons involved in a process, like in a reduction, and it's going to convert it into what's called coulombs, which is a unit of charge. That then gets converted into an electrical measurement, which is an amp. That's the amount of electrons flowing, and it's at a particular rate, so it's per second. And what this is basically saying is that to take the number of Faradays that are required, or the amount of electrical current that's required, or the number of electrons that are required in order to reduce, say, a cation that has one positive charge, or one that has two positive charges, or one that has three positive charges. You see, you're going to need one electron, two electrons, three electrons to get all of these to the place where they are solid. They no longer have a charge. And so the relationship would go like that. B would be more than A, and C would be more than B. So if you know the charge, you can say something about how much electricity would be required, how many Faradays would be required. Okay, we are getting very close. Oh no, I was thinking, no, we're not very close to the end. We still got quite a bit to do. This next slide, we started this back in the thermochemistry chapter, of where we were relating Gibbs free energy and equilibrium constant. And remember, we said that, I think I'll type this in. Let's try it here. That the Gibbs free energy and the equilibrium constant are inversely related. That is, that to get a negative Gibbs free energy, and therefore making it spontaneous, we would want to have a very large and positive, so very big and positive value for the equilibrium constant. Now we have something new to put into consideration, and that is the cell potential. And when we're comparing the cell potential to the equilibrium constant, you can see that there's no negative. There's a whole bunch, there's a function going on here, but there's no change in sign. So what that's telling us then is that there's a direct relationship between the cell potential and the equilibrium constant. So to have the reaction spontaneously go to the product, you would also have a large positive value for the cell potential. So cell potential, oops, get my marker going. Cell potential is going to be positive, and the equilibrium constant is going to be large and positive. And then finally, here at the bottom, we've got a relationship between the Gibbs free energy and the cell potential. So we're back to having a negative in there. So we're back to it being inverse. Oh, that didn't work. Oh, maybe it did work. I don't know. Let me see. Nope, it didn't work. Okay, I was trying to copy and paste, but it didn't work. So I have to type it. So there's an inverse relationship once again, that to get a spontaneous process, you need a negative Gibbs free energy, and you would also then need a positive cell potential. Now that's written out here below for Gibbs free energy to be spontaneous, then it would be negative. It'd be less than 0. And also for it to be spontaneous, and now since we're looking at it from an electrochemical standpoint, it's a voltaic cell, then it's going to be positive. See, greater than 0. And then it's the opposite when it's non-spontaneous. And like we said before, when it's non-spontaneous, we also call that electrolytic. Okay, anybody got a question about this? So what we now is look at some examples of batteries that are using, voltaic cells. So first one up is the most simplest, well, not really the most simplest. The most simplest is the voltaic cells like we were just looking at. But the most practical version of this is the zinc carbon dry cell. So we don't have any liquid involved. It's just dry materials. But you still have a cathode where the reduction is occurring, and you still have an anode where oxidation is occurring. The anode in this case is this carbon rod that touches the top of the battery, and the cathode is a paste of manganese oxide, ammonium chloride, zinc chloride, all this stuff in here. And also there's a metal bottom here. And so that's what comprises then our cathode. So you still have the same components as in our voltaic cells. You still have an anode and a cathode. Okay? Now we'll look at a little bit more modern technology, and that is the alkaline cell. And again, you've got a cathode where there's a reduction. You've got, they're going to call it a current collector. It's an anode, and that's where your oxidation occurs. And that current collector is this metal rod that goes in the middle here. And then our cathode is a manganese oxide powder combined with coal dust. Anyway, it's this stuff out here. Okay. Now moving along to another example, the NiCad batteries, which was really the first of our really modern batteries that were rechargeable. And here you've got repeated layers of cathode node. So it's repeating over and over again as we go through here. So it's anode, cathode, back and forth, back and forth, back and forth. So that allows you to pack a lot of capacity into a fairly small package. And then the most modern battery is the lithium ion battery. This is responsible for some technology, electric vehicles. And in this case, things are working a little bit differently because instead of having electrons moving around in the cell, we have moving electron holes. These are the absence of an electron. So we have a moving absence of an electron. It's not really like a positive charge. It's more like this is where an electron can be, but it's not. And that's moving, and that creates the current. Kind of a weird idea. Okay, let's look at one more type of battery. This is going actually backwards as far as being modern. This has been around for a long time, and that is the lead acid battery. This is what is in your automobile battery. Excuse me, guys. Let me see. I think that's, no, that's nothing. Okay, this is what's in your automobile. So you have an anode where you're doing your oxidation. You have a cathode where you're doing your reduction. The anode has lead dioxide in there, and then your cathode is pieces of lead. So as it says, it's a lead acid battery. You have in there sulfuric acid. Now, you may have heard about if you have lost a charge on your battery and someone is going to jump your battery, that you've got to be very careful, because if you try to recharge this quickly, it will produce a lot of hydrogen gas, which, if given a spark, will explode. And when you get that explosion, you also have sulfuric acid around. So the battery could break open and spray sulfuric acid all over you. So what you want to do if you're going to be charging from another battery in another car is, first off, make sure that the other car is not running. You don't want it to be going when they're doing it. But you would first connect your wire between the positive connectors on both of the batteries, the one that's charging and the one that you're charging from. Then in your car, the negative terminal should be going to what they call ground. I'll do the symbol for ground. It's like a little triangle made out of lines, but it should be attached to a metal part in your automobile. So what you would do then is, from the charging automobile, you would run the cable over to another location that is ground, or another metal part of your car, but you want this connection to be away from the battery. So the first thing you're doing is connecting the two positives together, then you're connecting the negative from the battery you're charging from to a metal location on your car, away from the battery. So if there's a spark or something, it's not going to ignite the hydrogen gas. This is seriously a very dangerous thing to be doing, and you want to really be careful. Definitely do not attach positive to negative between the batteries. That will destroy your battery, probably destroy the other person's battery, seriously mess up your automobile. Once you have them hooked up, then the person that has the good battery can start their car and give it a while then for your battery to be pulled up to where it can then start your car. Okay, just wanted to take this opportunity to keep you guys safe. Okay, so now we're going to change technologies. We're going to go from batteries to fuel cells. Fuel cells are a really neat gadget in that you can put in, say, hydrogen gas, or you could put in methane, CH4, in other words, natural gas, the same stuff we use in Bunsen burners. And then we can put in oxygen. And many times the oxygen is just the air in the atmosphere. And when you combine those together, you get a continuous production of electricity. So this will continue to produce electricity as long as you're supplying it with a fuel like hydrogen or methane, and it has a source of air or oxygen. Unlike a battery, you don't have to recharge it, you don't have to replace it necessarily unless it breaks. There is still an anode that does an oxidation, there's still a cathode that does a reduction, but it's just that this process is continuous. It's not like with a battery where you cannot be using it and charging it simultaneously. I realize we have an alternator in a car. It's not really recharging the battery so much as it's keeping everything running. Well, it depends. At night, it's you're sort of at a break even because you're running your lights. During the day, you would be recharging it. So, um, people can buy these and use it to get electricity for their home and get off the grid. In some cases, it's economically advantageous to do. There was a attempt to make a fuel cell laptop computer where you would put in a fuel cartridge and it would use air, use the oxygen in the air, and it would make electricity. But it never really caught on. But they did try. And there are fuel cell automobiles also. Now, one other aspect of electrochemistry is the process of corrosion. And corrosion, you know, rusting sounds like, hey, that's not all that big a deal, but it results in a lot of cost to maintain various things outside where you have exposure to water and possibly to salt. Salt will amplify the process. But we have here a piece of iron, and on the outside of the iron, we have a paint layer up there. And as long as the paint layer never gets a hole in it, everything's good. But as soon as you get a break, like here where it's the cathode, or on the other side here where it's the anode, now the water can get contact with the iron or the steel on the inside. And at the cathode side, then you're going to be getting a reduction going from oxygen. And on the other side, you're going to be getting an oxidation, which that's the biggest problem. The iron is going to be oxidizing and it's going to be producing rust. So you're going to wind up with Fe2 plus combined with oxygen, combined with an oxide. So one way of trying to avoid this is with the coatings on the outside. Another way is this next slide. It's called cathodic protection. The way this is working is we have an object that we're trying to protect. So that's what is over here. So we've got a fuel storage container in the ground, or you've got a bridge support like on the expressway where we're got bridges, and we bury a anode that it says is a sacrificial anode. So frequently this is a piece of magnesium. And then we just hook a wire between the two. And so then the electrons are going to flow from the metal that we're trying to protect over to the anode. And then the anode will eventually be gone. It will eventually be converted into magnesium oxide. but it will have prevented our metal object from rusting. And so then, every so often we'll have to come back and replace the sacrificial anode because we've consumed it. So anyway, sometimes when you're driving, if you're stuck in traffic, you might notice what looks like a wire that's attached to one of the bridge supports, and it is going to the ground, and it's going to a piece of magnesium that's buried in the ground. And so they're using that along with painting the structures to try to keep them from rusting. But obviously, it's really a hard thing to do because there's still plenty of rust. Okay, so that is the last slide. Has anybody got a question on any of this stuff? Okay, then what I'd like for us to end up with is this other worksheet. So I'm going to pull this down, put up the other worksheet, put you guys back in your groups and let you work on it. Okay, so I'm going to take this down. The other worksheet is over in Blackboard if you guys want to go get it there. I'm going to display it here though. And it's on using the Nernst equation in order to calculate a potential where the concentration is not 1 molar. So you see, we're using the same reaction we used before, Fe3 plus going to Fe2 plus. We have our concentrations. I'll tell you what, I think rather than putting you guys into groups, I'm just going to let you guys work this, and then I'll call on someone and see what you got. So anyway, you've got given here, you've got the Nernst equation, which is what you're going to need to find the answer. You've got the reaction up here. You've got the original standard potential, and you've got the concentrations. So why don't you take a moment and try to figure out what the answer is here, and then I'll ask somebody for that answer. Okay? So I'll give you, I don't know, 3 minutes or so to do this in. Okay, guys. So we're wanting to get the new potential here, and there's two pieces that are going to be necessary to do that. One is to figure out, well, what's the value of n, so that we can put it in the equation right here. And the next is, what is the value of q? And then we're going to be taking the log of q, and then that'll go into our equation right here. Okay? So I'm going to randomly select somebody to ask them what the value of n is. Step, what did you get for n? I'll try chat. Okay, I'm going to pass that to someone else. Although, let's see. Oh, we still got somebody that got booted out. I keep getting the booted out people. Oh, here we go. Hey, Erica, what'd you get for n, please? Oh, uh-oh. That's not good. Okay, I'm going to back up and go to chat. Okay. It's a good thing we're going over this thing then. So we look at our equation up here, and n is the number of electrons that is being transferred. So number of electrons. So now looking at this equation here, Erica, how many electrons are we adding? Yeah, one. So it's the coefficient for the electron. So we'll write that over here. Now I'm going to ask somebody for what they think Q is. Lily, what do you think Q is?
let me see here. It's 3 times 10 to the negative fifth because you do the 9.0 times 10 to the negative fifth over 3.
Okay, so 3 times 10 to the negative fifth is what you were saying.
Yes.
Okay, let's see
That
if
is Q.
let's see what the rest of these guys think. Does anybody not agree with 3 times 10 to the negative fifth? Anybody want to see how she got it, just so in case you're not sure? Oh, well, that's good. Sounds like everybody's got it. So, I mean, we're taking the products over the reactants. So the product is the Fe2 plus. So we're taking the concentration to Fe2 plus, and we're dividing it by the concentration of the reactant. The reactant's the Fe3 plus. So we're just taking the 9 times 10 to the negative fifth and dividing it by 3, and you wind up with 3 times 10 to the negative fifth. Okay, super. So now we just need to take the log of that. I'll ask somebody. I want to make sure they're still here. Yep. Okay. I lost a few of you guys. So from Sada, what do you think the log of Q is going to be? What's the log of 3 times 10 to the negative 5? Negative 4.52. Anybody not agree? Okay, so it looks like we're good there. So if we fill in our numbers, the value for E is 0.77. We're going to subtract from that 0.0592, and N is 1, so it's really just going to be 0.0592. And then we're going to multiply that times the log of Q, which is the negative 4.52. So what do you guys think is the final answer then? I'm just going to text it. I'll just anybody want to try it. What do you think the answer is? Yes, Lily, what do you think the answer is?
I got 1.03775, so it was 1.04.
1.04.
But I did a bigger, or I didn't round for the Q, the log of Q, like I wrote out more.
Yeah, well, don't, yeah, because you don't want to really, yeah, you want to carry all the digits. So does anybody disagree with the 1.04 for your answer? Well, I think you're good. No one's disagreeing with you, so it must be true. Anyhow, okay, guys. Anybody have a question about anything? Okay, then in that case, I will see you on Monday. We'll do another lab. Now, that one really will be our last lab. So we'll do that on Monday. And can't think of anything else. So if anything comes up that you need, please email me and I'll see if I can take care of it. So otherwise, you guys have a good evening. Do your best to be safe, and I'll see you on Monday then. So have a good